Okay, so section 9.3 deals with the dot product. If you took linear algebra, you would have seen the dot product. It's sometimes called the inner product. But to motivate the definition of a dot product, I want to do an example, another physics example. So let me give you a moment to copy this example down. Okay, so in this problem, we have a crate that's hauled 8 meters up a ramp under a constant force of 200 newtons applied at an angle of 25 degrees to the ramp. And we want to find the work done. We want to find the work done. Okay, so, well, all right. How is work defined? How do we define work, W? Good, Ryan. Good, Ryan. Force times distance. Both Ryans. Good. Now, work can be measured in joules or foot-pounds, and you'll have problems with both of those. This problem is going to, work will be eventually measured in joules because force is in newtons. All right, so what's the, I mean, this problem isn't like, you know, pushing a box along a flat horizontal surface. We're a crate's being hauled up a ramp. So what would be helpful to start this problem off? What do we definitely need to help us? Yeah, well, the angle is 25 degrees to the ramp, but the ramp itself, it's not, oh my, well, I'll tell you, let me draw a picture here. That's okay. We're getting some good participation here. Let's draw a sketch, as Robin suggested. Okay, I'm going to draw a sketch here. There's my ramp. And I'm applying a force to move this crate up the ramp. So the crate starts there and ends up here, a distance of 8 meters. And I just drew a ramp. The ramp The ramp actually, it's not, I want to be careful how I phrase this. It's not relevant, how high the ramp is. What matters is the angle of the force being applied. That is, well, I want to be a little bit careful here. I want to be a little bit careful because I know you're thinking gravity and all that. I want to be careful about, what I say. But what moves the crate along the ramp? What moves that? Well, it's a force that is parallel to the ramp. So you have this force here. You have this force. That's right, Christopher. You have this force that's being applied. Maybe they're using a rope to hold the crate up the ramp, but the rope is being held at 25 degrees angle to the ramp. But the part of the force that's doing the work is the component of the force that's parallel to the ramp. And that's the force. When we compute work equals force times distance, we need the magnitude of the force that's parallel to the ramp. And so we have to figure out, all right, well, I'm going to draw a right triangle here from the force down to the ramp, and this value of x, this horizontal component of that force, which is parallel to the ramp, is what I'm interested in. So the cosine of 25 degrees is x over the magnitude of the force. And so x is equal to the magnitude of the force times the cosine of 25 degrees. That's the component of the force. That's the component of the force that does the work in moving the crate up the ramp. Are there any questions on that? It's a force is it's the push or pull going in the direction of the ramp that's moving that crate. So okay, work is force times distance. That's the basic definition. But the force that is relevant here, the component of the force that does the work, is the magnitude of the force vector times the cosine of 25 degrees times the distance. Well, the distance, I'm drawing another vector here, a d vector, that has a magnitude of 8 meters. Okay, it has a magnitude of 8 meters, and it's the ramp itself. But it's not the full ramp. It's just it's a distance. It's a distance vector. Okay, on the ramp, and so work is equal to the magnitude of the force times the magnitude of the distance vector on the ramp times the cosine of 20 degrees. And that's how the dot product is defined. The dot product, if you look in the book, A dot B, and we draw a nice solid dot because we don't want to get confused with multiplication. A dot B, okay, let me just try to make that dot a little bit nicer. This is where I think the stylus would help a little bit, things like this, but we're good. A dot B is equal to the magnitude, it's defined as the magnitude of the A vector times the magnitude of the B vector times the cosine of the angle between vectors A and B. And I like to think of that definition as being inspired by finding the work. Because really, in finding the work, all we're doing is computing the dot product between the force vector and the distance vector. And when you work that out, you're going to get 1,450 Newton meters, which is 1,450 joules. That is the work that was done. Okay, are there any questions on that? Is there ever a time when the dot product, when this dot product would equal 0? I mean, let's assume that vectors A and B are not 0 vectors. Let's assume they are vectors that have some length to them. Okay, some length, some magnitude. What would theta have to be for the dot product to equal 0? That's right, Eric. That's right, John. 90 degrees. 90 degrees. And in fact, when the dot product between two vectors equals 90 degrees, what do we say about those vectors? We call those vectors what type of vectors? Does anyone know? There's a term, it begins with an O.
It's like orthogonal or something?
That's right. That's right. Good, John. Orthogonal vectors. That's right. And at this point, let me bring up the ebook. Hold on here. We're in chapter 9. Let me bring up. So now we're going to go into the ebook and look at a few things here. So let me do that. Hold on, there was a comment. Oh, hold on. One moment. Yeah, hold on, Christian. I can go back to the previous slide. One moment. There we go. All right, yeah, let me know, class, when you're ready for me to move on. You're welcome, Christian. By the way, what did I use to draw this beautiful picture? What did we use? What did I use here? What special tool? A ruler. All right. So, well, no, I didn't use the mouse, Christian, to draw that. I used a ruler to draw that. I mean, so rulers can be helpful for to draw pictures. How many of you have rulers maybe collecting a little bit of dust in your desks at home? Okay, well, it's on your desk. I like that, Christopher. All right, so make use of your rulers and protractors. Why not? Okay, now wait, hold on. I got to go back here. Let me go back into all right, into the ebook. Okay, so good, it's showing. Right. So we went through this. Here's the definition of the dot product. And okay, we basically covered this kind of thing, but here they mentioned that if a dot product equals 0, the only way that can happen is if the angle between the vectors is 90 degrees. And that means the vectors are orthogonal. They're perpendicular to each other. Okay, so that's a result. That's good to know. Now, the way the dot product is defined here, this definition involves knowing the angle between the two vectors, but sometimes it can be difficult finding the angle between two vectors. If it's given to you, it's nice. But if it's not given to you, how can we compute the dot product? Well, they give the dot product in what's called component form. So in this case, they have two three-dimensional vectors, okay, and A and B. And it can be shown, it's not hard to show, but it can be shown that the dot product between two vectors is equal to A1 times B1 plus A2 times B2 plus A3 times B3. They use the law of cosines to show that, which you maybe have seen in pre-calculus. Right now, I'm just worried about looking at the results. How many have maybe seen this definition of a dot product before? Maybe in another class. Okay, Eric's seen it, and Deodath has. Okay, all right, very good, very good. So this is really not hard to compute a dot product. It's just simple. I mean, in example 3, they give simple example there. Where they computed 3 dot products. I hope that's not hard. I think that's pretty straightforward. But if there are any questions, please ask. Example 4, show that two vectors are perpendicular. Well, showing the two vectors are perpendicular amounts to showing that the dot product equals 0. So not hard, not hard. Example 5, they want you to find the angle between two vectors. Okay, so here you're given two vectors in three-dimensional space, and you want to find the angle between those vectors. Okay, so you can understand that's an important problem to be able to do. Okay, so what you do is you have to use the two definitions of the dot product to get to the answer. First of all, you compute the dot product using the dot product in component form. And we find that the dot product between these two vectors A and B is equal to 2. Okay. Well, we also know, though, that the cosine of theta from the other definition of the dot product, since A dot B equals the length of A times the length of B times the cosine of theta, this means the cosine of theta is equal to the dot product divided by the product of those lengths. And we can get the lengths of the vectors. We know they're 3 and root 38. And so the cosine of theta would be 2 over 3 times root 38. And that means the angle between A and B would be the inverse cosine of 2 times 2 divided by 3 square root of 38. Okay. Okay, and you'll get 84 degrees then. Okay, are there any questions on that? Okay, all right. Well, then moving on, because I wanna hopefully you'll have a little time to work on your section 9.3 assignment. So moving on here, they talk a little bit about projections. Now, projections really are used a lot in linear algebra, but they're used other places as well. And, they talk about vector projections. So, what does a vector projection mean? In figure 5, they show two examples of vector projections. And what it is you take a vector. You have two vectors. You have a vector you have a vector A and a vector B. Look at in figure 5, the top picture. So what you're doing is you're taking the vector B and you're basically slamming it down into the vector A. You're projecting the vector B onto A. And that red vector that results is called your projection of the vector B onto the vector A. That's what that is. In the second picture, you have a vector B and a vector A. And again, they're slamming the vector B right down into the vector A. And so you'll get the projection of the vector B onto the vector A. That's how a projection vector is defined. Has anybody seen projections in maybe one of their other classes? Projection vectors? Okay, Christopher has. Robin, Eric. Okay, all right. So very good, very good. Well, they show in the book they have formulas. They have formulas for the component of the projection vector and then the actual projection vector itself. Okay, and I'm just trying to think here. I guess it isn't too hard to show it. They have here, I mean, basically the scalar projection, if you look at the projection, like here in figure 6, if you look at the projection of the vector B onto A, the magnitude of that projection vector would be the magnitude of the vector B times the cosine of theta, because the cosine of theta is equal to the length of the adjacent side of that right triangle over the magnitude of the hypotenuse, or length of the hypotenuse, which would be the length of the vector B. And so the projection vector then would have to have length given by the length of B times the cosine of theta. And so that's how you get your component of the projection vector. Okay, that's how you get your component. And then, of course, the projection vector is going to be this component. Well, I got to be a little bit careful here. I got to be a little bit careful. We're not quite done yet. Not quite done. Let me just see here, one moment. Yeah, so by virtue of the definition of the dot product, the fact that A dot B equals the magnitude of A, or the length of A times the length of B times the cosine of theta, then the length of B times the cosine of theta, that component, is equal to the dot product of A and B divided by the length of A, which is, and that's how you get the component of they call it the scalar projection of B onto A. It's that scalar. And then the vector projection of B onto A would just be the component of the scalar projection of B onto A times a vector that points in the direction of A, of the vector A, and it's the unit that they use, it would be the unit vector, A over the length of A. So that's how you get those formulas. They're pretty straightforward. I mean, you're going to apply them. Are there any questions on that in general? All right, I'm going to stop the recording.